Instruments like this, with strings, obviously need several components. The strings themselves are the basic things that are producing the sound. They're long and thin. Then they need flat plates to help to amplify, and then they need hollow shells underneath. And so we're going to be talking to begin with about long, thin, one-dimensional things, two-dimensional flat things, and three-dimensional volumes. Now, to begin with, we're going to do an experiment, a very elegant experiment, I think, that was done by John Tyndall, one of the former directors of the RI here, in the middle of the 19th century. What we're going to do is to heat up this wire. I'm going to ask Bryson to pass a current through it, and we shall begin to see it glow. And then once it's started to glow, we're going to make it oscillate, to vibrate. And I think we can perhaps see it vibrating, first of all, rather slowly. And we're going to put the lights down a bit so that you can see it better. And I think we shall find that as it vibrates, this part here, which is vibrating quite a lot, is cooling. And the parts at the end, which aren't vibrating so strongly, are glowing. Now, if we can increase the speed of the oscillation, we shall find that we get a second pattern, a second mode, as we call it, twice the frequency. And now these are the two bits that are cooling, and we've got a hot bit at the middle and a hot bit at each end. We call those nodes, points of no displacement. Now if we up the frequency to 3 times the original one, I think we shall find that we get 3 places where it's cooling rapidly, and we've got 2 places there and 1 at each end where nothing very much is happening. Now, I think that's a very pretty demonstration. John Tyndall was very keen that everybody should see exactly what was happening, and it's certainly easier to see that than if you're just looking at an ordinary wire. Well, now, we need to ask ourselves, what would be the notes associated with those particular patterns? And I'm going to go over here to the synthesizer, which we've set up to produce a series of single notes. And we're going to use this instrument over here. This is a real-time analyzer. And on the screen, when I play one of these notes, we shall find that there's 1, or in this case 2, of the lines pop up. Now I'm going to move up with the series of notes that we would get if we had the string vibrating in the basic note, and then twice the frequency, 3 times, 4 times, and so on. There's the first one, there's the second one, there's the third. I'll do them separately to begin with. 4th, 5th, 6th, 7th, 8th, 9th, and 10th. So you can see that what the instrument is doing is it's picking out the various components, drawing, as it were, a map of them. And if I play them all together, you can see we have a rich pattern of sound, and we have a lot of frequencies on the screen. The other point, while we're just looking at it, is that these so-called harmonics are getting closer together as we go up the scale. Well, now I said that we were going to go from strings to flat things. And the experiment I want to do now was first done a long, long time ago by a man called Chladni, C-H-L-A-D-N-I. It's interesting because he was a scientist who deliberately set out to be famous, I suppose lots of people would do that in other areas, but it's unusual for a scientist to do something just because he wanted to be famous. This is a metal plate. If I hit it, I think you can hear that there are lots and lots of different sounds there. But if instead of hitting it, I hold it and bow it, I can pick out just one of them. And by bowing it and holding it in various ways, I can produce a lot of separate notes. Now, Chladni's idea was that if you scattered sand on the plate, then the sand would dance around, and just as we had on the string, we had points where nothing much was happening. On a plate, we're going to have lines where nothing much is happening. Now, I'm going to try to bow this plate in such a way that we shall get a St. Andrew's cross and then a semicircle on each of the four sides of the plate. And to do that, I have to put two fingers there and bow it in this position. And the sand dances around and collects in the right place. Well, now, I've kept my fingers on there so that you can see that by putting that finger, I've made those lines, and by putting that one there, I've made that line. Now I want to add a St. George's cross, partly because I'm English, but for other reasons as well. And if we add a St. George's cross, what I need to do is to use three fingers. And putting a finger there will force the St. George's cross. And now I have to bow in between. Now, if I leave the sand on, it will tend, although it's very light, to make the plate go back into the original pattern. So I'm going to put some fresh sand on, put three fingers down and bow it there. And we get the St. George's cross. Well, now, there are loads of patterns you can get with this, and each one has a different note. And as we go up the scale, the notes get higher. But they're not related in the same way that the notes were on the string. They're very complicated relationships which we don't need to go into. I'm just going to do one more pattern. It's a favourite of mine because, quite honestly, I don't really understand how it works. What I'm going to try to do is to get a circle with some radial lines as well. And in order to do that, I have to put my fingers somewhere about there and bow it. No, wrong one. There it is. That's it. Well, that's one way of producing patterns on a plate. Another way is to use a technique that we call holography. I'm sure you've met holograms, laser holograms, and if you are making a hologram of something that's moving, rather complicated things happen, because when the plate is vibrating, suppose it's vibrating like that, you're really going to get two holograms, because a lot of the time the plate's going to be like that, and a lot of the time it's going to be like that, and you get two holograms, and that produces some rather strange optical effects called interference, and we shall see on the picture that we get all these fringes here, but in particular you can see we've got the pattern that I had at the beginning, the St. Andrew's cross and the three semicircles. These are some holograms that were made by my friend Bernard Richardson. Now, the second pattern shows the addition of the St. George's cross. There are differences, of course, but I think you can see the nodal lines. And I think the third one shows my circular pattern. So we can produce them in that sort of way. Now, they're very pretty patterns, but it's really quite difficult to imagine. I mean, it's easy enough to imagine that if it was doing that, we'd have a line there. But how can you imagine the sort of complications that you would run into in trying to get the plate to vibrate to produce a circle or the St. Andrew's cross? Well, Bernard has also done some computer animations. And we're going to run a sequence now in which the computer has worked out what the pattern ought to be for the plates. And we're going to start with the plate stationary and then run through the sequence. There you can see the plate vibrating with the, although it doesn't look as though it's moving at all, when I bow it, it is actually doing that. This is the next one up. This is the St. George's cross. You can see there's a fixed point there now. And it gives you a much better idea of the actually complicated things that the plate is doing in order to produce those patterns. The plate looks very rigid, but in fact it's bending quite a lot. And our plates can be used for all sorts of purposes. We can use it, as I said, as amplifiers, but they can also be musical instruments. This, in fact, is a Celeste, and I'm going to ask Paul, if we can find him. Where is he? There he is. If Paul would come along and play it for us. There's a stool to sit on. Would you like to just play a scale to begin with? It's rather like a mechanized glockenspiel. The glockenspiel, you hammer with hammers, but here, when you strike the keys, these wires and so on operate the hammers. Now, could you just play something? Well, perhaps you could just play one note, first of all, and that's the one that's being played. And I think if we have a close look at that, you can see those grey things are the plates. And just tap it a few times, would you? That's it, lovely. And you can probably see the hammer moving. Now, if you could just play as a little piece, we can see what the hammers are doing. Thank you, Paul. Well, now, another musical instrument that is a plate of sorts is this one. This is just an ordinary household saw, and if I hit it, it doesn't really sound musical at all. What I've got to do, first of all, is to bend it. If I bend it like that, it's quite dead. But if I bend it into an S shape, immediately it springs to life. There it's dead, there it's lively. In order to make music with it, I have to use a bow. This is a small violin bow. If I bend it into the S shape, we get a note. And we can change the pitch. Now, this instrument, if we can call it that, was very popular in Edwardian times. And they used to use it for playing romantic love songs. And for that, you need excessive vibrato. And you get that by letting your right heel wobble. That sort of thing. Well, I thought it would be rather fun to be a two-man band for once. So on this clavier here, I've recorded a little bit of an accompaniment, and I'll see if I can play a little tune. Well, now we're going to move on from plates. We're going to think what happens if you begin to fold up the edges of a plate. If you fold up the edges of a plate, you arrive at something like this. I'm very fond of referring to John Tyndall, and this is another of his pieces of apparatus. He used it for a variety of reasons. And if we just hit it with a hammer or a mallet, we can get rather a nice sound. Now, the trouble is, I want to show you how it's vibrating, and I need 3 hands. So I wonder if somebody along here, would you like to? Yes, you come out and help me with this. I want somebody strong. What I'd like you to do is to use that part of the mallet and give it a really good bash, really hard. I'm going to hold it there. Give it a good bash. can you do it, sort of hit it about there? Okay? Jolly good. Now what I'm going to do is to put a little pith ball there, and can you see how it's dancing? You can tell that the plate is vibrating, and if I go over here, it's also vibrating, but if I go about a quarter of the way around, would you like to give it another bash? Jolly good. If I go about a quarter of the way around, it isn't vibrating as much, and yet there, it's vibrating a lot. And if we had time, we could go around, and we should find that the four places opposite where you hit it, and the other two quadrants there, would be vibrating very strongly, and a quarter of the way in between them, half the way in between them rather, it wouldn't be vibrating much at all. So it's really doing something like that, going into an oval, another one, and so on like that. Okay, thank you very much indeed, that's great. Well now, bowls like that, and the Chladni plate, are producing mixtures of notes which are not in the ordinary sort of harmonic ratios that we expect. And one of the characteristics of that is that it doesn't sound very much like a sort of Western instrument. It's an instrument that is very common in Southeast Asia, and there are all sorts of gongs and things that are used down there. And we're going to see a Gamelan orchestra. In fact, it's a British one at the University of York. And once it's started, we're going then to look at some dancers in Java dancing to the Gamelan music. You saw all sorts of gongs and bowls and so on and so forth, all producing rather interesting sounds. Well, now, if we were to carry on still further, we folded up the plate. If we now completely close it, we end up with something, this is on a different scale, but we end up with something like this. This is, in fact, what's called a Helmholtz resonator, and it actually responds to only one note. In fact, it just happens by coincidence that this fork has the same note as this Helmholtz resonator. And if I put it in front like that, I think you can hear the resonator responding. Now, Helmholtz resonators crop up in all sorts of instruments, and in particular, they crop up in the human voice. I don't know whether you're aware of the fact that your mouth is really a Helmholtz resonator. This is a little electric razor, and I'm going to turn on my microphone here. I'm going to put the razor on my cheek, and then I'm going to alter the shape of the cavity, and it's going to pick out notes from the razor, and I think you'll hear them quite clearly. It looks rather silly, but but it's a good way of demonstrating a Helmholtz resonator. It's a pity that we haven't time to talk more about the voice, but in a way I'm quite relieved because I don't really know all that much about the human voice, although it is a marvellous instrument. Well, we've seen how plates behave, we've seen how volumes behave, and I think we can now begin to turn to the main subject for today, which is how the string instruments work. This, as I'm sure you are aware, is a lute. Lutes have been known for thousands of years in all kinds of forms. We think they started probably in the Middle East, and in fact it's been suggested that the name lute is really a corruption of the Arabic al-ud. But whether that is the case or not, I don't know. You can argue for hours and hours on that sort of point. What is true is that it's a very beautiful instrument. It's very, very light. It's as light as a feather. And it's this body, the pear-shaped body, that's doing the amplification. And here we have the hole out of which the sound comes, and you see the very beautiful decoration there. Now, you remember I was altering the aperture of my mouth to alter the pitch of the sound, and the actual amount of space in that pattern is very important. That's what determines the pitch of the resonance. And it's the same, in fact, in the guitar, which is a much later development. This is a very simple guitar, and it's got a big hole in the center, and the diameter of that hole is crucial in determining the pitch at which resonance is going to occur. Well, now, Dominic is going to come down and just sort of play a little bit on this modern guitar for a moment. I hasten to add that it's not his own guitar, it's one that we provided, so it may not be awfully good, but we'll see. Well, thank you very much indeed, that was great. Now what we're going to do is we're going to do some scientific experiments on the guitar. Bryson is going to adjust this analyzer. I'll come round here, go there. Now, would you like to just play on the... No, I'd better stop talking because the microphone's picking up my voice. When I stop, if you could play a note, and Bryson will freeze it. Well, now you can see that there's the sort of fundamental frequency, and these are the various harmonics. And now what I want to do is to show you how plucking the strings at different places changes the amount of the various harmonics. Could you pluck it now somewhere near the middle, as near the middle as you can? Well, you can see there we've got two very strong things and a few things here. Now could you pluck it, just wait till I stop talking and then pluck it right near the bridge. Now do you see how we've got far more components, and so we're going to get a different mixture, a different sound. Now in fact there are lots of other ways. By plucking it in different directions you can alter the quality of the sound. And in fact some people have described the guitar as one of the most flexible instruments in the world because you can make it sound like almost anything. Unfortunately we haven't time to listen to that. Thank you very much indeed, Dominic. Now, of course, I don't want to give the impression that the only instruments that are of interest are from the Western world. And we've invited a lady from Japan to come and demonstrate to us a Japanese plucked instrument. She is Mrs. Ayako Lister, and she's going to bring in her koto, which is a very long instrument. It's a sort of mixture of body and neck all in one, and it's got a complicated system of strings and bridges, and I think it makes a most wonderful and beautiful sound, and we'll ask Mrs. Lister if she'll play to us. Thank you very much indeed. Well, you noticed quite a lot of, apart from the interesting and beautiful music, you probably noticed all sorts of interesting operations going on, changing the pitch, adding the vibrato by moving up and down on the strings and so on. There's a whole lot of physics that, if we had time, we could discuss. There's one point that arose out of the koto and the guitar, and that is that the body of the player plays a very important part. And this is a hologram which my friend John Tyra made, and I think you can see that as this person plucks the guitar, you can see the vibration fringes on the guitar, but you can also see vibrations on the arm and on the body of the player. And this is a very important point. In nearly all musical instruments it happens. The vibrations travel up the arms and so on and so forth. And so the actual positions and so on of the arms are much more important than you'd imagine. They can alter the whole quality of the sound. Well, now, as I say, we're going to turn to the bowed instruments. And I'd like, first of all, to show you an outline drawing of some rather ancient medieval type instruments. Well, this is a rather curious little fellow. And the interesting thing is that he's using his left hand to bow, and he's got his right hand up here, but the right hand seems to have the right arm seems to have a left hand on it. So it really is doing most peculiar things. The next slides show three different ways in which we can play instruments, and we don't really know how people played them in those days. Do you lean your head to the left or to the right? Do you bow near the neck or do you bow near the middle? So we just don't know. We have to rely on these sort of drawings. There are three main kinds of origins. This one at this end is called a fidel. The one at the other end is called a rebec. And the one in the middle is probably slightly more familiar. That, in fact, is a viol. And we shall be talking a bit more about viols in a moment. So we don't know exactly how they developed, but we do know that in the 400 or 500 years ago, this sort of instrument was very common. This is a small viol. You can see that it's different from a violin in that it has C holes instead of the F holes. And if you look sideways on, I think you can see that the back is flat, whereas a violin has a bowed back. It also has sloping shoulders. Now, there are many different sizes of viol, and in fact, one of the biggest ones we still use in the orchestra today, and that's the double bass. If you look at a double bass, it has sloping shoulders, whereas a violin and a cello have right-angle shoulders there. Now, the other thing is that it's very much deeper. So the resonance of the body is going to be a much lower pitch than the violin. Well, I thought it might be interesting just to hear a little bit of the sort of sound that viols would make. They don't play on their own. They tend to play in a group, and we talk about a case of viols or a consort of viols. And here's just a little bit of music of the sort that they would have played. Well, the main feature of that is that it's very quiet. So the viol is very much a sort of instrument that you play at home in a small group. In those days, at the time when the viol was popular, the violin was already in existence, but it was a rather crude instrument. It was the sort of thing that you played to accompany folk dancing, jigs, that sort of thing. Rather a coarse instrument. But then, eventually, around about, I suppose, the middle of the 17th century, the violin began to develop in prominence because people wanted a bit louder sounds, and the viol started to decay. And in Pepys' diary, there's a splendid quotation. It's an anonymous little verse that Pepys picked out. In former days we had the viol in, ere the true instrument had come about, but now we say, since this all ears do win, the violin hath put the viol out. And indeed, the violin did begin to put the viol out. But it wasn't this one. It wasn't this modern one. It was this kind of violin, which is a Baroque instrument. It differs from a modern violin in that the fingerboard is shorter and the neck is set at a less steep angle. And in fact, all the great violins made by Stradivari and Amati and all the other great makers of the Cremona school, all were made in this style. But then, when the great symphonies of Beethoven and Brahms came along, the sort of early part of the 19th century, around about 1830, I suppose, people wanted much louder instruments. And so the old Baroque instruments were rebuilt. They were given a longer fingerboard, the neck was set further back, so you could have rather thicker strings and greater tension. And in fact, all the great Stradivari violins and the Amatis and the Guarneris and so on have all been rebuilt. And so we never really hear them sounding exactly as they used to do. But the body, of course, is the important thing. It's the body that produces the quality of sound, and that, of course, still stays the same. Well, now, we're going to do one or two scientific experiments on violins at this point, and I'm going to ask Naomi Thomas, if she would, to come and help us. She's going to, first of all, play just a little bit on her own violin so that we can hear what a good violin sounds like, because in a moment we're going to use a rather less good one. Well, that's a lovely sound. Thank you very much. Now, if we could put that down, what we're going to do now is to use this violin, which is not a very good one. In fact, if it was a good one, we wouldn't have done the horrible things that we've done to it. We're going to, we've got all sorts of wires hitched up to it, which are going to get in the way when Naomi tries to play it. But in particular, it's got a removable sound post. Now, I'll explain exactly what the sound post is in a moment, but could you just play on the G string, I think, will be the best. Now, I'm going to remove the sound post with this little gadget here. If I put the screw in there, you can't do this with an ordinary violin, of course. It would be really pretty disastrous. And there, in fact, is the sound post that I've taken out. And now I'm going to ask Naomi to play it again. I don't think you'll hear very much difference, but we did this a day or two ago, and we recorded the result on this instrument, and in a moment we'll see it on the screen. Would you like to play that for me? You can, if you listen very carefully, tell some differences, but if we look at the pattern, this white blocked pattern is the response curve of the violin without the sound post, and this is the one with the sound post. And you can see how all this extra volume, as it were, and all these lower frequencies have been added in. So it's a much richer sort of sound when we have the sound post there. Thank you very much indeed. That's great. When a violin maker wants to make a really good instrument, he takes something like a Strad or an Amati or a Guarneri, and he measures very, very carefully all the dimensions. Now, in a real violin, in a good violin, of course, the body is not only arched, but the thickness varies all the way along. If we were to be able to put in a micrometer and measure, we should find the thickness is varying all the way along. And so what they do is they try to match the dimensions, all the measurements, as precisely as possible to the nearest thousandth of an inch. And having done that, they then expect that it will be a good violin. And very often it isn't. And the reason it isn't is that the wood is not the same. And in fact, even if you take two pieces of wood from the same plank, from the same tree, side by side, the properties are a little bit different. So when you make it up into a violin, even though the sizes and dimensions may be exactly like a Strad, it doesn't sound like one. And I want to do a couple of experiments just to show you how wood varies. Here are two pieces of wood which were made up for me by Bernard Richardson in Cardiff. They're exactly the same shape and size, same thickness and everything. But if I put them together like that and apply the same sort of force to both of them, I think you can see that the bottom one is bending far, far more than the top one. That's really quite extraordinary. In fact, that one is really quite flexible. It doesn't break, and this one is quite difficult to bend. And yet, the grain is running the same way. But if I hold them like this, I think you'll be able to see that the grain on one of them, on the flexible one, the bottom one, is running at 45 degrees, and the grain on the top one is running absolutely at right angles to the surface. And just that slight change in grain is enough to make all that difference in flexibility. Now, there's another important point about wood. You might say, well, if wood is such a problem, why don't we use plastic? Well, of course, we could use plastic, and in fact, there have been plastic violins, but they're never very successful because it seems that the actual properties, the elastic properties of wood, play a very important part. Now, I'm going to do an experiment with this piece of wood, which is rather like the Chladni plate, but I'm using some sort of glitter stuff to put on it, which is a bit lighter than sand. And I'm going to ask Bryson to drive this. There's a loudspeaker underneath. And I think you can see we've got a very simple pattern. Obviously, this bit's going down, this is going up, and that's going down, and those are the two nodal lines. Now, that was around about between 80 and 90 hertz. Okay, well now I'm going to get rid of that glitter, and I'm going to turn the plate the other way. Now the grain is running that way. Originally it was that way. I'm going to put glitter on again. Oops, too much, sorry. I'm going to put glitter on again, and this time we're going to have to go much higher in frequency to find a place where it will resonate. There it is. There. Now that's what, 300 and something? Yes, it's nearly 4 times the frequency, and yet it's the same modal pattern. And that tells us that the velocity of sound in the direction across the grain is far lower. Across the grain is only about a quarter of the velocity along the grain. Well, it has been suggested that that is why most of the instruments that we use in the orchestra are roughly 4 times longer than they are wide. Because then if you start a sound somewhere about here, travelling across the grain, it's going to travel more slowly, and travelling along the grain, it's going to travel faster. But whether that is the case, I'm not really sure. There are all sorts of arguments that could go on almost indefinitely about that sort of thing. Well, now we need to, at some stage, discuss what we really mean by a good violin. What do we mean by the best violin? The problem is that if you took a whole lot of violins and you asked a number of players to try them all, you would probably come up with different answers. They'd all agree that that one is pretty bad. They'd all agree, I'm sure, that Naomi's violin is a good one. But in between, there'd be a whole spectrum which the people would argue about. And part of the difficulty is the human brain. It seems a bit silly to say it, but the human brain does get in the way of making judgments of that kind, because you tend to become programmed. A violinist will be so used to playing his or her own violin that when they pick up another one, they won't perhaps get the best out of it. And it really takes several months to get used to a violin. So it's no use just asking somebody to pick up 3 or 4 violins and try them. You won't get a very good answer. So if the players can't agree, it's not too surprising that the scientists can't agree either, because we don't really know what is wanted. Well, now, there was a great physicist called Saunders who also happened to be a very good viola player in America. And he started to do some measurements, scientific measurements, to try to get some relationship between what the players said and what the scientists said. And one of the things he did was to get a violinist to play a scale starting at the bottom and to play each note as loud as he possibly could. And then he measured the loudness with a microphone, and this is the sort of result you get for a fairly good violin. And this is the one you get for a very bad violin. And I think you can notice that with the bad violin, we've got some peaks and troughs. We've got some here as well. It's not uniform, but the bad violin is much more irregular than the good one. So you might argue from that if you had a completely uniform response, then that would be the best violin of all. Well, you can get completely uniform response. That's what happens if you use an electric violin. You have an amplifier in the violin. And it sounds awful. It doesn't sound remotely like a good violin. So we have a problem. It's a philosophical problem, really. The sort of question we might ask is, if Stradivari had been an electronic engineer instead of a superb craftsman, would we now prefer electronic violins to wooden ones? I suspect the answer is no, because I think, in fact I'm sure, that the brain likes a little bit of irregularity. It doesn't like things to be too uniform. We like little differences. We like little bits of disharmony. And this is what, as it were, keeps the brain awake when we're listening to music. If things are too uniform, the brain tends to sort of switch off and say, oh, this is boring. Well, that's only my point of view. But it is quite an interesting thing to argue about. Now, there are other sorts of tests we can do, and I'm going to ask Naomi, if she will, to come down again. And we're going to do another test using this violin. And what we've done is we've hitched it up to a number of electrical devices. That's what all these wires are for. The first one here actually measures the force that the string is exerting on the bridge. So that's where we start. Then we've got here a thing called an accelerometer. I'm sure you've all been in a car or a bus when somebody's put the brakes on hard and you all go move to the front. Well, inside here is a little weight, and when the body moves up and down, the weight moves up and down inside. I'm not sure exactly what happens there, but it produces electrical signals. And then the third thing we're going to do, if you could hold it, thank you, Naomi. The third thing we're going to do is to put on the microphone. And on the screen in a moment, we shall see 3 oscillograph traces. The top one is going to be the force on the bridge. The second one is going to be the response of the body from the accelerometer. And the bottom one is going to be what comes out. You can see it on my voice is operating the thing at the bottom. So I'm going to shut up and ask Naomi to play on the bottom string. Lovely. Now, I think you can probably see that on the top one, we've got a curve like that. The string is being displaced and then jumping back, displaced, jumping back. On the middle one, that's quite different. So the bridge is exerting a force on the body, but the body is changing it. And that's why the body is so important. And then the body is radiating the sound, and it's changed again. Can we do just a couple of notes again to see that? Well, that's fine. Now you can see that the bottom one is totally different from what the string is doing. And it doesn't matter what note you're playing, the string pattern is much the same, but the body is changing it completely. Thank you very much indeed, Naomi. That's great. Well, now, of course, we've been sticking to rather small instruments at the moment. I'd like to just have a look at a larger one. And Anne, I think, is going to come out, and we've got her cello tucked away somewhere, and she's going to play just a little bit for us. The problems of the cello are much the same as those of the violin. It's the problems of getting the body right to give the right amplification. And Anne is just going to let us hear what her cello sounds like, first of all. very much indeed, and I think we ought to thank the music rest as well. Useful to have movable music rests. Now what I would like to do is just do a little experiment with you. I've mentioned the F-holes in the violin. Of course they look rather pretty, but of course the thing that matters is the actual area of the hole. Just as you remember when I opened my mouth and shut it, we got different resonances. So what I'm going to try to do is to get Anne to play on the D string, and then I'm going to put my hands over the hole and see if we can hear a difference in the sound. I'm not sure whether you could hear it. I could hear it. It certainly goes louder, that's the main thing. And if we were able to analyse it with the analyzer, we'd probably find that the quality has changed as well. Thank you very much indeed, Anne. Well, now I'd like to go back just briefly to the guitar. We have looked at some holograms of various things, the Chladni plate and so on. I'd like to just now show you a hologram of a guitar plate vibrating. And what is happening is that this part of the body is coming up, when that goes down, and then that comes up and that goes down, and we have a line where nothing much is happening there. Now, this is holography. We've seen various varieties of that, and we also saw at the beginning the variations in the vibrations of a plate done by computer simulation, the Chladni plate. We're now going to run a sequence of computer simulation of what happens in a guitar. Now the guitar body seems to be very solid, and yet when it starts vibrating, this of course is magnified greatly, but that's what's happening in the lowest frequencies of a guitar. It's really quite astonishing, isn't it, that the solid plate is vibrating like that. This has been computed by my colleague Bernard Richardson and some of his students. Now this one is very like the hologram we had a moment ago. You can see the two halves going up and down. And Gordon Walker and Matthew Brook have also been involved in the very complicated calculations that have to be done. And I think we have, in a moment, one more mode. There we have another, even more complicated mode. And this is happening all the time when the guitar is being played. I'm not sure whether guitar players are aware of that fact, but it is really quite extraordinary what goes on. Finally, I think I'm going to mention this electric guitar. It's very like an ordinary guitar as far as the strings are concerned, but of course it doesn't have a body. Instead of having the hollow body to magnify the sound, to amplify it, it has this rather solid piece of wood, and then it's got some pickups here, and all of the electrical output of the pickups goes into our mixer here. And if I turn up the guitar, well, I'll pluck the string first of all to show you that we don't get much sound. And now if I turn up the pickup, there I think you can hear that there's a very big increase in volume. Enormous changes in volume. And of course we can also alter the tone. I'll pluck the string. You can hear variations in the tone, and of course if I operate this, you can introduce vibrato as well. So there are all sorts of things you can do that are interesting. There are more complicated guitars than this, which really completely convert the sound into something else. In fact, they are really almost like synthesizers, which use the string as the basic source of the sound, and then all the computer electronics and so on convert it into quite different sounds. Well, now we're going to turn from these sort of things to the mechanized strings. And by mechanized strings, what I really mean is things like the Clavichord and the Harpsichord, things of that kind. And the first one is a clavichord. In the clavichord, we have a series of strings which are connected to a sound box. Now, if I pluck the string, it sounds very dull because of all this damping, this red felt. When we're actually using the clavichord, if I press one of the keys, for instance that one, you can see this little hammer comes up, and when it's up, it becomes a bridge. And so it's this length of string from here to the bridge that is sounding, and the other half is damped by the red felt. Now, in order to economize, instead of having one hammer for every string, which would mean 3 times as many strings as we have here, we have 3 hammers striking the same string. Now, if I go to the next note up, we have a shorter length, and if I go to the next note down, we have a longer length. So those are the 3 hammers which are all striking the same string. And it's the same all the way through, and the tuning process involves bending the hammers slightly in order to make sure that they are at the right distance from the center one. Now, I think Thomas is going to come and play a little bit for us so that we can hear the kind of tone. I should say that this is very useful if you live in a flat, because it doesn't annoy the neighbours too much. Thank you very much indeed. That's great. Now, the harpsichord, the clavichord is a very quiet instrument. If we go to the next loudest sort of instruments, that's the harpsichords and the spinets, where instead of hitting the string, we actually pluck it. And this is a model of the harpsichord mechanism. Here's the string. I don't know whether you can see that little black thing there. That's a piece of goose quill or something of that kind. And this green thing is a damper which falls back. Now, if I press the key, I don't know whether you can see that the goose quill plucked the string, and each time I play it, it plucks the string, and then the damper falls back. And now exactly that sort of mechanism is incorporated in this rather beautiful spinet that has been lent to us. And Sarah, where is she? There she is going to just demonstrate the instrument by playing just a scale or two for us. And you can watch these little things, these jacks as they're called, going up and down, plucking the strings. Just once more, I think. Fine. Well, thank you. Now, will you stay there? Because I think we've got something else for you to do in a moment or two. Well, the other kind of keyboard instrument that has become very popular recently is the synthesizer. We're going to be spending more time on that later on, but for the moment, I'm going to adjust this one so that it turns into a kind of harpsichord. And Rajan is going to come and play it for us. And what I want you to notice is that the synthesizer is not only imitating the sound, but it's also imitating even the sort of rattle as the jacks and the keys move up and down. Shall I hold that for you? That might be the easiest way. Oh, that. Thank you very much indeed. That's great. Now, you probably noticed that that was a rather richer sound, because in a harpsichord you often have 3 or 4 keyboards. Well, now what I hope has emerged from what I've said today is what an incredibly complicated family the string family is. We have plucked strings, we have bowed strings, but we're still only on the absolute fringe of development. Scientifically speaking, I think we're beginning to help makers to achieve more uniform instruments. We're not necessarily helping them all to achieve the quality of a Strad, for example, because we frankly don't know what the real quality of a Strad is. I'm going to stop at that point, and the next time we meet, we're going to be transferring to the wind instruments. But before we do that, we're going to ask Sarah if she would play us out with a little tune on the spinet.
Thank you.